Good afternoon. Let's get started. Welcome everybody to our webinar today. I am Patrick Campbell, the Associate Director at our new Center for Satellite Earth Science Research at George Mason University. We're happy to have today Professor Michael Vermeuel from Purdue University to talk to us about some of his research on surface atmospheric exchange processes and trace gases through different environments. I'm very excited to hear about this. Working with Michael right now on, as mentioned before, but biogenic emission model and comparing to some of his measurements and flux measurements and force canopies. So I'm very excited that he's here to talk to us about some of his new measurements he has and how it can relate to some of the work that we do in our center and beyond, such as air quality modeling or atmospheric composition modeling, can lead to a lot of improvements there. So I'm going to start with an introduction for Professor Michael Vermeuel. He joined Purdue University in the Department of Earth, Atmospheric, and Planetary Sciences as an assistant professor in August of 2024. His research leverages novel mass spectrometry approaches for detecting reactive gases near the Earth's surface, which influence air quality, climate, and the natural ecosystems. Using a combination of field observations, chemical transport modeling, and laboratory studies, his lab seeks to advance our understanding of the sources and fates of both well-known and newly identified atmospheric chemicals. And before joining Purdue, Michael was a postdoctoral associate at the University of Minnesota and Colorado State University. He earned his PhD in chemistry from the University of Wisconsin-Madison, where he developed field-deployable mass spectrometry methods for detecting VOCs, ozone, and key inorganics in real time, and applied them to observe these species over forests, lakes, Pacific coast, and urban areas. And in 2024, Michael received the American Geophysical Union's, AGU's, James R. Holton Award, which honors outstanding scientific achievements from individuals within 3 years of earning their PhD. So that's great. Outside of research, Michael enjoys hiking, playing guitar, and reading. And so with that, I'd like to welcome again, Michael, and I'll just give the floor to you to present. And I did talk to Michael. He said it's okay if we have some discussion as we go along. If there's any clarification questions, I'll keep an eye on the chat and we can ask some questions. So thanks again, Michael, and please take it away.
All right. Yeah, thanks for having me. And my talk should be around 45 minutes, but I'll definitely take any questions and we could go from there. So yeah, thanks again for having me. Thanks for the intro. I'm Michael. I am a
professor at Purdue University.
Yes. I'm a professor at Purdue University, assistant professor at Purdue University in Earth, Atmospheric, and Planetary Sciences. I'm going to present some work that is kind of work that I've done over the past 2 years, published over the past 2 years, and the newer work that I'm submitting soon. Mostly focused on the surface atmosphere exchange of reactive trace gases. So I currently am just spinning up a lab at Purdue. We're called the AirChem Lab, Atmospheric Integrated Research of Chemistry and Meteorology, because we like to use micrometeorological tools for measuring these fluxes of gases. So we use mass spectrometry, field and lab measurements, and different models. And I really like these Purdue colors. I'm a little spooked out by the mascot, though. So I don't know if any of you all follow NCAA sports, but Purdue Pete has been voted the creepiest and second worst mascot in the NCAA. I did take a look at your mascot, and I do like it's the Patriot, I believe. So I do want to give kind of like a very broad overview, and I know there are atmospheric chemists in the group, but just what I mean by reactive trace gases. So as Patrick had mentioned, I'm mostly interested in ozone and VOCs. So ozone, as we know, is a major pollutant. It itself is a greenhouse gas, but it also causes damages to plants through the stomatal uptake that causes billions of dollars in annual agricultural losses. And it also leads to respiratory and cardiovascular disease. So there's an estimated 365,000 premature COP deaths globally per year from ozone, from elevated ozone. And ozone is removed from the atmosphere either through chemical reactions, so about 80% through chemical reactions, and then also through dry deposition, this physical uptake to surfaces, either taken up by plants, soils, water, urban grime, whatever's around. Ozone itself is not emitted from the surface, it's removed, but it's produced from precursors, VOC and NOx. So these are two gases that undergo bidirectional exchange. They could be emitted or deposited to the surface. Nitrogen oxides, NOx, are made up of nitrogen dioxide and nitric oxide, but VOCs can make up to 100,000 other species. That's what's estimated to be in the atmosphere. And when VOCs and NOx are in the presence of HOx, so the hydroxyl radical, the VOC reacts with hydroxyl radical to make a hydroperoxy radical. That reacts with nitric oxide to make NO2. That NO2 is photolyzed, combines with O2 to make ozone. So these are all coupled important processes. Ozone can also react with VOC and NOx through chemical loss. So it's produced by these species. It could be lost by reaction with these species. And when ozone reacts with VOCs, can make these low volatility oxidized species that can nucleate and condense and make secondary organic aerosol, which directly and indirectly modify climate because they scatter sunlight directly or make clouds that scatter sunlight. So the very broad view is it's really important to measure VOCs and ozone and evaluate models and how we're representing these species for understanding atmospheric composition, air quality, and climate. So our work seeks to close knowledge gaps regarding how that bidirectional exchange is affecting reactive trace gases, so VOCs and ozone. So I just have this little schematic here with key knowledge gaps. So what our group wants to know is what controls the surface-atmosphere exchange, this emission or deposition of VOCs and ozone, how much of which gases undergo this exchange. So like I said, there's 10 to the 5th VOCs that could be exchanging with the surface. I want to know which ones they are and how that affects atmospheric composition, which is critical in modifying leading to chemical reactions that then has feedbacks on atmospheric composition. And then what are some inferences we could make for air quality and climate. So to address that, our group makes direct observations of trace gases using eddy covariance. So we use mass spectrometry and an eddy covariance system, which I'll explain more later. And then we incorporate that data into models of different scales to evaluate chemical processes. So different scales, meaning we could have a partial trajectory model over Lake Michigan, where we're inputting VOC emissions and NOx emissions into the start of this plume and letting it go throughout the Lake Michigan coast, or global larger scale models like geochem, chemical transport models. And our group focuses on two broad themes for understanding the link of chemistry and surface-atmosphere exchange and micrometeorology. So the first is quantifying VOCs and their drivers. And by drivers, I mean, I guess the external variables that are controlling these fluxes. So there can be dependencies of these fluxes on temperature, humidity, solar radiation, leaf stage, so leaf phenology, winds, driving this bidirectional exchange of VOCs in biogenic and anthropogenic spheres. And then closure of the ozone budget itself. So it's one molecule, it should be easy to figure out, but it's really not, because there are all these components contributing to the scalar conservation of this species. So if we can measure concentrations and fluxes, how well could we understand this budget? And then so results from our work, so we collect data, we share the data, we also use this data to improve model constraints of how we treat surface-atmosphere exchange. So we both want to improve our understanding of these processes, but actually improve our real simulations of these processes. So we do both. So for today's seminar, I just want to briefly go over some methods for detecting trace gases and our models, then go through my research themes. So one focusing on the biogenic VOCs, they're focusing on anthropogenic, and then a little bit on closure of surface-atmosphere exchange of ozone. So we'll start with our observational methods. So we measure gases in the atmosphere using chemical ionization mass spectrometry. So this is an online real-time detection method of VOCs, ozone, inorganics. And the way that this operates is that we are quantifying gases based on their mass. So we draw in ambient air through the front end of our instrument. So this is just sampling outdoors through this reaction chamber, stage 1. Then we put in a reagent ion also into the reaction chamber, and those two, the reagent ion and our ambient air mixture, will react to make some charged product. And that reagent ion that we choose depends on what kind of species we want to measure. So proton transfer reaction mass spectrometry is very commonly used to measure VOCs through proton transfer, H+. So we make a hydronium ion, and then if a VOC has a higher proton affinity, so it wants to take that H+ away from the H3O+ more than the H3O+ wants to hold on to it, then we will detect a VOC with a hydrogen on it. So we'll make a charged product. Another way of measuring species is using iodide anion chemical ionization mass spec, where that is a negatively charged iodide, which is able to coordinate and form an adduct with species that have hydrogen that allow for hydrogen bonding. So like an oxygenated VOC will just like stick to the iodide. And then the same goes for ozone. So we can detect ozone that way. So we generate charged products. They make its way through the mass spec. And then those species, it's kind of a beam of ions is pulsed through this time of flight mass spectrometer, where we are separating the gases based on their mass. So based on the time it takes for a gas to arrive at a detector. And what we get out is a spectrum. That is really, we have on the x-axis mass to charge ratio, but really that's the time it takes for a gas to arrive at a detector, and we could change that to mass. And what we get out are thousands of peaks for individual species, and they're all either ambient VOCs, things that were generated inside of the instrument, all kinds of things that are up to interpretation. But what I want to do is be able to pull out which species are actual VOCs. So for example, we know that ethanol, its mass will be around 47.01. We could isolate that one peak. We could fit the peak, integrate it, so get the area under the curve and calibrate it so that we know what areas correspond to what concentrations. And then we get out a time series where we're actually able to visualize and quantify VOCs. So for ethanol, we see it go away during the day because of photochemistry, but also more because of mixing, because we have an expanding boundary layer. And then at night, we have the nocturnal boundary layer that's keeping that ethanol near the surface. And then during the day, it's mixed out again. And we're able to get this more longer term synoptic variability from, fronts coming in, warming of the surface. Skip that. So we use this SIMS method because it could collect many spectra a second, so up to 40,000 spectra a second. But we average it down to 10 hertz, so we could use the eddy covariance method to directly quantify fluxes. So what the eddy covariance method is doing is taking advantage of the fact that we have vertical wind, so these turbulent eddies that are transporting gases to and from the surface. So we could approximate these circular moving spheres, moving gases above and below. And what we do is we quantify covariances in wind and concentration. So seeing instantaneous deviations from a mean of winds and of concentration over some averaging period. And taking that product over some averaging period gives you a flux. Didn't really want to go through the advection diffusion equation, but more physically, we could think of it as this way. If we were to have an inlet that is co-located with our wind sensor, so that's a sonic anemometer, we run that inlet all the way down to the base of our trailer, and we're able to make co-located measurements. So for example, if I were to have an ethanol-rich air parcel ejected from a canopy, and then that makes its way to my measurement axis, then I'll have an upward perturbation in winds, I'll have an upward perturbation in concentrations. If this is happening more often than not, then we would have an emission. Conversely, if I were to have parcels, downward trajectory parcels making its way to my measurement axis that's containing ethanol, then I'll have a downward perturbation in winds and a positive perturbation in ethanol. And if that happens more often than not, where we're constantly having eddies bring ethanol down to the surface, then that would be a deposition. And then finally, we couple observations with models for applications across different scales. Maybe many of you are familiar with box modeling, where we're just solving series of differential equations, accounting for sources and sinks, and we could include detailed chemistry because this is dimensionless. So if we want to interpret field observations, we could use this for our localized measurements. Our group also uses one-dimensional vertical canopy models, which we could approximate maybe as boxes kind of stacked on each other now. So we're still having a lot of dimensionless parameterized processes, but now we're solving for vertical exchange across the boxes themselves. So you're solving for turbulent diffusion. And then stepping up, we also use chemical transport models. So GeoChem primarily, which is a global 3D simulation, slowest with the simplest chemistry, but now we can interpret more global budgets of atmospheric species, chemical lifetimes, wanting to know what the lifetime of methane is, how much isoprene is emitted, all of that. So moving on to some applications of these. So we're pretty focused on biogenic VOCs because they provide a really major control on atmospheric chemistry. They make up the majority of VOC emissions from the surface to the atmosphere. So depending on which end you want to look at anthropogenic emissions, the terrestrial biosphere emits up to an order of magnitude more of reactive carbon per year than anthropogenic sources. And then BVOCs also make up the majority of VOC reactions. So in this case, if you just weight the VOC fluxes by the reaction rate constant against OH, we could think of what the consequence of emitting a VOC into the atmosphere and being able to react is. 95% of that emitted reactivity is from biogenic sources in North America. And these are for model estimations, but observations show that models may be missing some species because observations of VOC fluxes show that there are way more species observed than in models. So there's about 40 VOCs in biogenic flux models, but observations show over 400 species over an orange orchard. And then there was also observations over a deciduous forest showing around 377 VOCs. So from those specific studies that I'm showing up here, a majority of these VOC mass, maybe not the species, but the total mass, is from species in models, but these are limited to just 2 locations using just one instrument. So the question is, how well are we simulating these drivers in atmospheric models? So I was part of this flux closure study where we tried to measure all the VOCs we could over this ponderosa pine plantation in the Colorado Front Range. So this is an application of what I was showing in the cartoon, where we're running an inlet up a tower, about a 30-meter tower above the forest floor. And we had inlets in a gradient measuring concentrations throughout the canopy and above. And then we had 3 stations where we had sonic anemometers to measure wind profiles. And then we were able to measure fluxes as well. And here are the mass specs at the base. So we had 2 mass specs at the base of our tower, one PTRMS and one ISIMS, the 2 methods that I was explaining before. And across these 2 methods, these 2 full spectra should capture nearly all of the gas phase organic carbon and reactivity against OH, so in the gas phase. So the hypothesis was that we should be able to, if we were to have these 2, we should be able to account for everything. So we used this and collected this data set and then tested the geochem chemical transport model to see exactly what we're missing and what the consequences are. So here are some results. So what I'm showing here on the left is this is all observations, a figure of unaccounted for VOC carbon flux and the number of ions you require to consider that flux. And I'm separating upward and downward flux because we saw bidirectional flux. And I have just here as an example. So for 90% of the upward flux, we needed only 23 ions. For 90% of the downward flux, we needed 125 ions. Using the 2 mass specs, we were able to quantify 1,300 or around 1,200 VOCs. But the ones that actually had detectable flux, we were able to quantify around 315, which is still more than the 40 in geochem. What we saw was the upward flux was dominated by a few species, which is consistent with the previous study. So only 2 species comprised about or greater than 60% of our VOC flux. And then most of that mass was from individually represented VOCs in chemical transport models. So species specific, we actually have most of the right ones that we need. But the downward flux was distributed among far more VOCs. And on top of that, few were actually explicitly individual modeled species. So rather than propanoic acid, it would be greater than C2 organic acid, something like that. So the majority of these species were what would be considered lump species. So the model mechanisms themselves need improvement because we're not getting representation of that downward flux very well. But the upward flux, we do, just from the species. Now, if we're to compare the actual mass fluxes, it's kind of reflected in how we're able to capture the species. So what I have here are the models and observations, model in red, observations in black of our fluxes for the net, upward and downward. So upward plus downward is net. And what we see for the upward is that the geochem model is capturing most of this, is capturing the net upward flux pretty well. There's a small at least for chemical transport models, a small model bias, so up to 25%. So we're doing the upward kind of well. But the downward is underestimated by greater than four times, primarily because of oxygenated VOCs that are missing from the chemical transport model. And these are transported and outsourced species that are made from like biomass burning plumes or oxidation products, so like isopoo or IUPOX, that are just not well accounted for. They're in the model, they're just not depositing well. So the conclusion here is that the PTRMS is capturing most of this net and upward flux pretty well, but the ISIMS is needed for understanding the downward flux, so the sink of these species, which include a lot of nitrogenated species. So more of these full spectral flux studies are required to understand this VOC fate. So this was the only study of its kind in a forest right now, but if you got two PTRs, two mass specs that you want to put together and go to another one, it would be great to evaluate more data sets. So thinking of the drivers of these fluxes, what's actually controlling this overestimate? So we see that surface temperature is a strong driver of VOC fluxes, which is what we expect. We model VOC fluxes in part using a temperature dependence, an exponential temperature dependence that's shown in this upper equation. And if we were to model or plot the observed fluxes against the temperature, we see an exponential dependence as we expect. But when we overlay our model fluxes in relation to the temperature, there's a sharp overestimate. So there's a steeper flux dependence on temperature in our model, which needs to be corrected. And then there were also other anomalies. Rain periods increase more reactive species. So what I'm showing here is a 2D plot of double bond equivalents and carbon oxidation state. More reactive species were emitted during rain periods, which there's only been like 1 or 2 studies that kind of hypothesize that like either the mechanical perturbation of the leaves themselves emit terpenoids or having like a wet film allows for faster transport to the surface because they don't want to be soluble in water. And then other species were suppressed because during rain periods, it was cloudy and cooler. And then during smoke periods, we saw an increase in deposited OVOC. So that's what's circled here. And these were species that were completely missing from the chemical transport model. So we need better temperature dependence, some rain parameterization, and then getting our smoke fluxes or our smoke VOCs better. There's one other study that's not from this flux study, but I could explain pretty quickly. That's leaf phenology, so like leaf life cycle, is also a driver of fluxes. So the year before this study, I was making measurements in northern Wisconsin over this mixed temperate forest. And during this time, we saw a very sharp change in leaf greenness throughout the study, like while we were there. So this is showing LAI, and then I got pictures. Pixar didn't happen of early September and later September. And I'm just showing here an example of monoterpene fluxes and monoterpene oxide fluxes throughout the study. And the period where we started to see leaf changing and leaf senescence, we got really high emissions. And if we were to overlay our Megan model, our geochem CTM over this, the temperatures went down and we had shorter days, so less sunlight. So we would expect that emissions would go down a lot. And that is what happened in the model, but in observations, there was a 4 times increase. So we didn't really have, we only had ecosystem scale data, so we can only really kind of talk to a forest ecologist and get an idea for what could be happening. But some potential causes is actually the desiccation itself releases BVOCs and the breaking up the leaf, or during the senescence process, the plants actually do produce antioxidants, and that would be reactive carbon to fight off this process. So there could be some release, but there's no leaf senescence mechanism in chemical transport models, so that's a missing source of reactive carbon for however long that stage is. So for this section, conclusions are we know which VOCs are important, but do not model them as well as we could. So in our pine forest, our upward flux was controlled by few species that are individually modeled, so that was not bad. But the downward flux, there were too many of them that we're not accounting for. In our forest, the net flux was dominated by upward emissions, which we would expect upward flux, and then the downward flux is grossly underestimated. And then there are mechanisms that are driving VOC fluxes not considered, so rain, leaf senescence. Okay, so moving on to the city, from the forest to the city, back to the forest, I want to talk about how we're quantifying anthropogenic VOCs. So in cities, inventories are very different, as we could expect, but fossil fuel emissions have long been the large contributor to VOC emissions, but these are changing due to better engineering standards like the catalytic converter that's reducing VOC fluxes, even though our vehicle miles traveled have increased. So we might be familiar that there's now a shift in the distribution of VOCs emitted, and now we're thinking that volatile chemical products such as fragrances, personal care products, adhesives are now a large part of this national inventory. But there are other things that could contribute to VOC emissions. So we know there's urban vegetation. So from the last part, we know that there are emissions of biogenic VOCs. So those would be a source of terpenoids, and that should be temperature dependent, which has been seen from an airborne flux study over LA that there are temperature dependencies. Emissions from buildings and degradation of materials. So if you have a higher density of buildings and those heat up, then you will get emissions out the attic. So one group from UC Berkeley, Betty Molyneux, published a paper pretty recently that showed that furfural and furanoids are a really good tracer for building emissions, attic emissions. And then cooking is another big one. So emissions of these N-aldehydes have been seen in Las Vegas, and now from a LA study, actually, that was published recently, that cooking should be a large part of this VOC budget in cities, so VCPs and cooking. So to check out if that's actually happening, we were part of this ground site for the NOAA aroma study called FROG New York, the fluxes of reactive organic gases in New York, and we made is pretty much the same study that we did in the pine forest, but now in Long Island, New York, Mineola, New York. So we had our two mass specs at the base of this cell tower. We stationed our eddy covariance system at 60 meters and 33 meters above the ground. And these two measurements, these two heights captured pretty different flux footprints. So all the area contained within these footprints is where we're measuring emissions from. So we saw residences, commercial plazas, restaurants, stores, mechanics in the Northeast. So there were commuters. There's a lot to capture here within this flux footprint that we saw. And we made measurements in the summertime, which is the summertime footprint that I'm showing here. And we also made measurements in the wintertime, see what happens when maybe commuting habits changed. Definitely the trees went away. It's not as warm anymore. There should be changes in the drivers. And that is what happened. We observed seasonality, seasonal variability in our VOC carbon fluxes. So what I'm showing here are the VOC carbon fluxes for the summer on top and the winter below. For our study, we see that there was almost a 2.5 to 3 times decrease in fluxes from the summer to the winter. There were also fewer VOCs measured. So in the summer, we measured 135 VOCs that were being emitted, and in the winter, we measured 53. And all VOC fluxes were upward, which is very different from the forest. This is just showing a diurnal profile for the summer and winter now across the two heights. And we could see that there was, seasonality looking at these diurnal profiles, but we can infer that they're due to, spatiotemporal variability that changes these. So there's time-based and spatial-based differences in these drivers. One is the measurement footprint. So as you go higher, you capture more sources that are they're spread out, but the diversity in sources changes. So there should be some difference across the 33 and 60 meter height. And then there are changes in environmental drivers. So you could maybe estimate that if we had changes in temperature, higher temperatures, maybe more biogenic emissions and more evaporative emissions too. So there's two different things that we have to look into. Looking at just the VOCs that were emitted across the two seasons, it's pretty much what we'd expect in these emissions inventories, which is pretty good, at least the key species. So ethanol was the primary contributor to emitted mass across the two studies. So I'm just showing here the mean fluxes throughout the study, and then their contribution to the cumulative flux, and then anything that's not in the top 10. So I just picked top 10 so we look at it easily. There were more biogenic species in the summer, so we saw isoprene and monoterpenes in higher amounts in the summertime. And then also looking at reactivity flux, weighting those by the reaction rate constant against OH. Isoprene was dominating this emitted reactivity, followed by ethanol. And then again, the reactivity got a lot lower in the winter time compared to the summer. So I'm just looking at the 8.4 versus the 2.4. But yeah, so the general is that many of these species are species that are in inventories. There was a very large drop in VOC fluxes and OH reactivity. And then, yeah, greater than 70% of the mass can be accounted for by only 10 molecules. So I got the time series, I got the general, the species that are contributing to it. Now I want to know what's actually controlling the observed variability. So I used a method that's very commonly used in chemical emissions inventories process evaluations, and that's positive matrix factorization. In this case, I used non-negative matrix factorization, which is almost exactly positive matrix factorization, except we're not weighting by errors. So what this does is decomposes a time series matrix into factors that control that variability. So I would input, and this could all be done in MATLAB, I input a matrix that is the VOCs, all 135 VOCs with time, and then CO and CO2 to see how that could explain variability because we measured fluxes of those. And then what I get out is a factor profile matrix, which I'll show an example of, and then a factor contribution matrix. And the number of factors that we have are the fewest number of factors to explain the flux variance. So here's what a factor profile matrix looks like. So it takes all the VOCs, finds relationships and finds variability, and puts out 5 different profiles that explain the variability in the flux. So we have 5 different sources or processes that contribute to the VOC flux. And then the factor contribution matrix is just here are all the VOCs that we're looking at, and then the larger and darker circles are the ones that most contribute to this factor variance. So if it's large and dark, then its time series looks most like one of those deal profiles. This is how you could estimate it. And then I'm able to take those factor profile matrices, factor contribution matrices. I also have to standardize the input matrix, so I'm not weighting by, since it was mostly ethanol, I don't want the output to just be ethanol. I could take the product of all of those again and get out a VOC carbon flux for the different flux factors. So now I have actual magnitudes that I could relate to the observed fluxes. So use PMF to break down the variability, got factor profiles, and now we have to understand what the heck these 5 profiles mean. So I'll just show a breakdown of the different factors. So the first one here's just an output of our time series and our factor contribution matrix. And what we saw is pretty evenly distributed VCP or VOCs across the board, with maybe some hot spots from like monoterpenes, monoterpenoids, some solvents. So what I attribute this to is I'm calling an area source VCP. So this is ubiquitous volatilization of these volatile chemical products. And the way that I kind of backed this out is I really just desperately tried to find any relationship between a meteorological variable that I could find for this time series. And what I found is that it correlated best when with latent heat or water flux over these more developed urban hardscapes rather than when it was over landscape residences. So that correlation fell out. And what I'm showing here is that since there's a better correlation over these hardscapes, over when the latent heat is evaporation dominated, we could assume that there is some relationship between evaporation of VOCs and evaporation of VCP of H2O. And then when we're transpiration dominated, then that falls apart. We also, if we're to look to the flux footprint where there's peak area VCP emissions, we see a strong contribution from this more developed Northwest. We also have fossil fuel traffic emission, which is this one was the easiest to figure out because all of the key contributors were traffic tracers. So benzene, aromatics, CO and CO2 were the strongest contributors to the variance as well. And then also the time series has rush hour peaks. So we're able to, when we're over the Northwest, when our density, flux footprint density is mostly over these intersections, we see the highest peaks in this emission. So area source VCPs, traffic, we have a biogenic residential flux. So that is that temperature dependent profile that I showed before. And a lot of the tracers are, again, biogenic species, so isoprene, methylvinyl ketone, methacrylin. But we also see emissions from those adducts that I was showing before. So we have our strongest contribution to the flux variance is furfural. So any air temperature dependent processes are linked into this flux. So that's why I'm calling it biogenic residential, because it's both trees and hot homes. And looking at the flux footprint, this was over the near southwest, where we're seeing a lot of landscaped residences. The next one, we saw highly variable near field solvent emissions. So this is from plumbing contractors, metal restoration. We saw acetone, toluenes, xylenes, and butyl acetate. These were all species that contribute that we would estimate as solvent emissions, but we're only to the northeast, so this is very spatially dependent when we're over there. So calling that point source VCPs. Yeah, it should be lumped in, but this is more, we're at the mercy of the footprint at this point. And then finally, the last one is from cooking. So these are higher molecular weight fatty acids when we're measuring over a McDonald's. So measuring to the northeast, and then some nitrogen-containing species from roasting when we're measuring over Portuguese barbecue, Churrascaria. So we're able to back those out. So here's just the summary of everything, putting all the fluxes together. We got the 5 different factor fluxes that I'm calling them, or flux factors, the key species contributing to them, and then, yeah, a breakdown, and I'll come back to these pie charts, a breakdown of the key contributors. We also made inferences for what these fluxes would be based on their day of week dependencies. So just showing the weekdays in colors, the weekend in black. And for the evaporative VCP temperature dependent sources, there was modest weekly patterns, kind of everything was within the uncertainty or the range of these deal profiles. And then in cooking and traffic, we see pretty strong weekday weekend differences. So for traffic, we see across the board emissions reduced. And then for cooking, we see a pretty stark change in where the peak emissions are. And then we repeated this for the wintertime. I won't go through this in too much detail, but we measured a lot fewer VOCs in the wintertime, so 53 versus 134. I actually called the study Froxical too, not my idea. We got, again, 5 factors that we're able to attribute to the same sources. So again, a traffic factor. This was most of the emissions now. Same tracers as the summer. Point source VCPs, so same peak, same species coming from the same region. Again, we have area of source VCPs, but this time the temperature is really reduced, so we're not having as strong a dependence on the surface temperature, which would be driving that gradient of surface temperature to air temperature would be driving this flux, and we don't have that as much anymore. We again have cooking, but the time series of the cooking has changed. And then a residential flux, but not a biogenic flux, just residential. So we again have that key tracer furfural, furanoids, and then follows calling a home heating pattern, but it could be up to interpretation if anyone has any idea for what could be causing a dip. So I didn't want to belabor the pie charts because I'm just going to show them here again anyway. So looking at the factor breakdowns across VOC carbon fluxes and reactivity flux, we see that, and I'm circling them in purple, these temperature-dependent VCP and biogenic emissions are a really important source of summertime emitted VOC mass and reactivity. So, you know, around 70% plus of each of them are from temperature-dependent sources. And those go away in the wintertime. In the wintertime, now we're shifting our dependence over to traffic. So since we reduced those temperature-dependent fluxes, we're now half of that flux in the wintertime is from traffic. And if I'm just comparing across the board the VOC fluxes for the different factors. I just highlighted the important things that I want to show. There's that huge drop in VCP fluxes across the summertime and wintertime, but a very small change in traffic, which makes sense because our traffic volume actually slightly decreases in the wintertime as well. People aren't traveling as much. And this is consistent with our carbon monoxide fluxes, which I'm showing here, where there is very small change across spring, summer, and winter for their deal profile. So we could say that this is a tracer for tailpipe emissions. So the takeaway, these temperature-dependent fluxes are going down in the wintertime. Traffic dependence does not go down by too much. So now we're shifting over to traffic. So the seasonality is controlled by surface temperatures. We compared these fluxes to a inventory called GRAPES, the Greenhouse Gas and Air Pollutant Emissions System inventory, which does not reproduce the seasonality at all. So I'm just showing the stacks of the different contributions in shaded colors to the VOC fluxes, and then our observations. And in dash, I removed the biogenic and Holmes factor because this is only an anthropogenic emissions inventory. So we see observations decrease by a factor of 2 for just anthropogenic across the summer and winter, but no seasonal dependence, barely any seasonal dependence in the inventory. And in the inventory, greater than 85% of these VCP is from VCPs and cooking, which is not what we saw. And then we see an underestimated contribution from traffic as well. So in our observations, we saw up to 50% in the wintertime. And in the inventory, we're seeing around 10 to 11%. So that's pretty different. So this lack of inventory seasonality is due to missing VCP temperature dependence. So there was reasonable agreement. So I'm showing here the VOC fluxes over the summer and winter, and then the reactivity again. I'll just focus on the VOC. We see in the summertime, there's actually not too bad of an agreement. In the wintertime, since there's that drop, and there's a missing inventory evaporative source mechanism, there's a pretty stark difference. There is a general underprediction of traffic VOCs, so we kind of, in this new inventory, are overcorrecting for traffic and for actually more for VCPs, and then also for cooking. So maybe traffic, that's kind of hard to pin down, but we are overcorrecting for what would be VCP and cooking in this region. That's mostly due to an overprescription of ethanol from cooking. So the cooking emissions inventory is primarily from measures in Las Vegas, and that in that was observations, there was a lot of ethanol, so they're kind of prescribing that. So in this section, we quantified many VOC sources within a footprint, and evaporative processes are generally misrepresented. So we observed a bunch of VOCs, broke them down into their sources of variability, saw primary sources, compared those across seasons. We saw enhanced fluxes due to the summer time evaporative and temperature dependent processes, and the seasonality is not captured in emissions inventories that are updated. So we need to have some better mechanism for these temperature dependent surface processes. Okay, and the last probably 6 or 7 minutes, looking at now ozone fluxes, completely shifting gears to VOCs. The same method, actually same detector really, but just different molecule. So deposition is a significant sink for tropospheric ozone, as I mentioned, but our chemical transport models need improvement in ozone uptake, and probably people are familiar with this idea. So ozone uptake to ecosystems, biogenic terrestrial ecosystems take place via dry deposition primarily. So you have turbulent transport of ozone to a canopy, you get uptake through stomata, loss to leaf cuticles, uptake to any surfaces, and then there could also be in-canopy chemistry that's occurring. And if your sensor is above your canopy and you're measuring flux, then you would be accounting for everything that's happening below your sensor. And I'll show a better physical description of that. And different chemical transport model treatments of this ozone deposition lead to pretty stark disparities. So this is just an intercomparison of 15 different chemical transport models over 3 different forests. And you can see differences in these these correlation coefficients and these slopes, the relationship of modeled and measured. So we need improvements. I think a lot of people are familiar with that idea. Part of that is because the parameterizations that we use for ozone deposition are very simplified. And we need that to be able to run our large global scale models efficiently. So in the GeosChem chemical transport model, we simulate ozone deposition using this big leaf parameterization, this dimensionless parameterization of this deposition velocity. So this VDO3, which is just the flux divided by the concentration. And we calculate this deposition velocity by really this algebraic parameterization as a function of temperature, sunlight, leaf area, wind speed, humidity, that's constrained by, at least in geochem, assimilated meteorology. So we have land surface maps, we have assimilated meteorology, we put all that together to get out a deposition velocity, and then we get a flux. But really, a better representation would be using something that's called a column model, where we're seeing changes, variability throughout a column because we have differences in leaf area density, shading, temperature, you have soil moisture, all different turbulent regimes throughout the canopy itself. So if you rearrange our scalar conservation, then we could get a flux as the summed components of deposition, chemistry, and storage or ventilation accumulation within a canopy. So column models, they're able to resolve canopy processes, but they don't have, you can't run a global column model unless you incorporate it into a larger scale chemical transport model. So something like a vertical model would be better at simulating ozone flux. So our question was, if we were to somehow find a way to couple a column model with a chemical transport model, will that improve chemical transport model predictions of ozone concentrations and ozone flux? So we used a bunch of different models to compare. We used just the GeoChem chemical transport model. So we're calling that GC in red. We use a vertical canopy model that's constrained by observations. So that is at least in this study, our best estimate for ozone fluxes. So that's constrained by all these meteorological environmental variables that drive that deposition velocity. And then our last is coupling this MLC Chem, Geos Chem, by constraining our model, our canopy model, by Geos Chem constraints. So by Geos Chem meteorology and chemical abundance. And we did this over 3 different forests that range in environmental conditions. So from least humid, arid, open canopy, different VOCs, all the way to very humid, dense canopy dominated by one VOC. These were just the names of the studies that I kind of showed at the beginning. And then I'm not going to show it to you, but we can assume that the GeoChem meteorology is capturing on average this observed meteorology. So it's doing a pretty good job, except for some points that I could point out. So running our column model constrained by GeoChem and comparing that to GeoChem. So here's some results. This is just a stack of deal profiles for flux of ozone, deposition velocity of ozone, surface ozone, and then within canopy ozone. And since GeoChem only has surface ozone and flux, I'll compare those. So to observations, so the flux, there's a 2 times overestimate because there's high surface ozone and then a 1.5 times overestimate in deposition velocity, so it's high. And then the surface ozone is also very high. So there's a 40% overestimate in surface ozone. And there's not a very large day-night difference for most of these because we don't actually have transport into the canopy. If we're to use our MLC model, so our best guess model, we have much better agreement. So those gold lines are overlapping with the black a lot better. But there are some periods where we're over-predicting nocturnal loss because of changes in relative humidity and mixing is what's happening. And then we have very small bias in canopy ozone. So we get in canopy ozone really well. And then finally, looking at this new coupled model, we get significant improvement relative to our GeoChem. So we see much better deposition velocities, and we actually are able to get day-night dynamics because of mixing that's occurring. So gold is best, blue is better, that we would actually be able to run online, and then GeoChem is just way over predicting everything. So what are the implications of this? So if we were with GeoChem, we can't really have an output as a good partitioning of loss within the canopy, but a vertical column we can. So for this MLC Chem model, we see that this non-stomatal uptake of ozone is up to 67% due to loss to cuticles or the ground. And in GeoChem, this is between 20 and 30%. So that means that the stomatal uptake in GeoChem is a lot higher than what would be our estimate, which we're saying is better, to which we can compare to observations better. So GeoChem is under-predicting non-stomatal uptake, over-predicting stomatal uptake. And then I mentioned that in-canopy chemistry is a portion of deposition velocities, but at least for our models, it's actually a small point. So for GeoChem, you don't really need to account for that. And then the last, I guess, taking this and seeing some actual ecosystem implications. The idea is GeoChem overestimates uptakes to plant stomata. And what that does is then overestimates our phytotoxicity estimates, or our predictions of phytotoxicity. So what I'm showing here is phytotoxic ozone dose per leaf area, which is just a metric for plant ozone uptake, which is summing up, taking the integral of ozone flux to model ozone flux normalized by leaf area index, and then not adding up the really, really small components. So just periods when there was really high stomatal uptake. So I'm just showing this here throughout the studies. For geochem, it's high. Observations, it's usually at the lower bound. And then if I extrapolate throughout the whole growing season, these are the values that I'm showing here. So we do have an observed that's calculated from this generally used Penman-Monteith inversion that's mostly dependent on heat fluxes. And then we could see that our observationally constrained MLC is doing a lot better at reproducing this phytotoxicity. Geochem overestimates it by a lot, so we're overestimating what that stomatal uptake and phytotoxicity would be, and then using our explicit canopy representation that brings us closer to observations, but our gold is always going to be the best because it uses actual observations. So what I'm showing here is that global ozone predictions from CTMs need work. We all probably have an idea of that. And being able to couple it to a resolved canopy will improve that, either this one or others. I know other groups are working on this as well. The CTMs overpredict ozone uptake, at least across these forests. A lot of that uptake should be from non-stomatal loss. And then that has implications for how we partition to loss to plants and phytotoxicity. Okay, so that was kind of blew through surface level, a lot of different studies that I did, but just put up some my contact information. Now I have a group that I'm leading. We're working on, we got our instrument, our mass spec, deploying it recently to an agricultural field. So we'll have results to show soon. And then just some other acknowledgements for people I've worked with, studies, and then funding. And I'll take any questions.